Okay, so today we're going to consolidate the things that we started on Thursday, which was talking about transformations. I just want to remind you about this link to the Desmos graph that we were playing with on Thursday. You can find it on D2L and click directly, or you could just type this in, and then you can play around with that Desmos graph and just remind yourself about how these transformations work. But you have already learned about most of these last year, so I'm just going to recap them real quick at the beginning. So this is what we did the other day, where we investigated together on Desmos and we consolidated, so I'm just going to go over it real fast. So the other day we talked about C and D, which are the numbers that are added at the end or added or subtracted on the inside. So whatever C is, whatever this number that's tacked on at the end is, if that number is positive, that means your whole function is going to move up. If the number is negative, that means the whole function is going to move down. For D, that's what moves things left and right. That's our horizontal shift. So if you see a positive D, you're actually going to move left, and if you see a negative D value, you're actually going to move right. So notice that your vertical stuff does exactly what you think it is. It says positive, goes up. It says negative, goes down. Those make sense in our brains. That's usually how we associate positive with up and negative with down. But with the horizontal changes, those are actually counterintuitive. So it says positive, but we're actually going to move left. And if it says negative, we're actually going to move right. Okay, so those are a little counterintuitive, but it's easy to remember that the vertical stuff always happens the way you predict, and the horizontal stuff always operates the opposite way. Okay, if you have very large or very small values for C and D, there's nothing special that happens because those values are large or small. So it's just whatever C is, move it up by that much, whatever D is, move it right by that much, etc. Okay, when we get into A and K though, that's when the size of the value matters, so that's why that stuff is there. So let's talk about A. So here we have A, D, and C. All three of those transformations you have learned about last year with quadratics. This year we're just expanding that to other functions as well, and then of course we're adding the horizontal change that I'll talk about in a sec. Alright, so if you have A, and A is a positive value, then you're not going to change anything because of its positivity. So don't change anything. But if A is negative, then you're going to have a reflection in the x-axis, which basically flips upside down. So that's a vertical flip because of A being negative. If A is a large number, so if it's greater than 1 or if it's less than -1, for example, 10, or 2 or 3, those are all larger than 1 or 2.5, or -3 or -4 or even -1.1. Those are all more negative than -1 or greater than +1. Then those will all cause vertical stretches. If your value of A is small, so between -1 and 1, so for example 0.2, -1 or -0.1, then you will have a vertical compression. K works the opposite way. So same thing at first. If you see a positive K, don't change anything. But if you see a negative, then you're going to have a reflection. But K, because it's horizontal, reflects things in the y-axis. So from left to right rather than the vertical change, which goes from up to down. And then if your K value is greater than 1, it actually does the opposite of what you think. So if it's greater than 1, then you actually have a horizontal compression. And if it's small, so between -1 and 1, then it actually causes a horizontal stretch. So notice that if you have a large A value, you have a vertical stretch. And if you have a small A value, you have a compression. Those seem to make sense. Large makes stretch, small makes compress. But the horizontal works the opposite way. With the horizontal, so that K value, if your K value is large, then you have a compression, and if that K value is small, so like a decimal number, you actually have a stretch. So counterintuitive. Okay, so in short, this is what your function would look like in function notation, where you have an A, K, D, and C all operating on this f of x. So at the heart of it, we have f of x with all these changes. Then what you could do is to apply your A, which causes the vertical stretch or reflection, you would take the y values and you'd multiply all of them by A. To apply K, which is your horizontal stretch or compression, you would take all of your x values and you would divide them by K. Easy to remember, y multiply by A, x divide by K. For D, you're going to do your horizontal shift. That one, because it's horizontal, you work with the x values, and you're going to add or subtract D, so opposite as you see it. So if it says x -2, you'll actually add 2. Or if it says x +5, you'll actually -5. And then for C, that's your vertical shift, or translation is another word for shift. And for that one, you're going to take your y values, and then you'll add C to them. And that's the same as you see it. So if it says positive 7, you're going to move the whole thing up 7. So notice that everything horizontal works the opposite way as what you would think, whereas all the vertical things do exactly what they say. So like this says A times F, you're just going to multiply A. And this says plus C, you're just going to add C. But this says minus D, you're actually going to add D, and this says multiply K, but you're actually going to divide K. So all of the horizontal stuff in the middle do the opposite of what it says. All the vertical stuff on the outside do exactly what it says. Okay. So here's an example. We're going to start by stating the parent function and then listing the transformations applied to it to obtain this crazy thing right here. So it looks pretty wild, but it's actually at the heart of it just a parabola. So I know it's a parabola because I see this x right here, and I see this square. And I know that that square is being applied to the x because the x is on the inside of the brackets. So because I have an x squared at the heart of this, no matter all these other factors and things that are being added and subtracted, at the heart of this, it is a quadratic. Okay, so the parent function is y equals x squared. All right. So the first thing that we're going to look at is this vertical reflection that's caused by this negative. Okay, so I'm going to always list my transformations and apply my transformations in left to right order. So the first thing on the left side is this negative, which is a vertical reflection. So that's a reflection in the x-axis. The next thing I want to look at is this 2/3. Now, because this is a value that's between, so this number is between -1 and +1. Like 2/3 is between, I'm sorry, I know this is ugly writing, but all I have at home is my mouse on my computer. So 2/3 is somewhere between -1 and +1. It's not larger than 1, it's not more negative than -1. So because of that, it is actually going to be a vertical compression. Okay, and we say the language is, we would say that it's a vertical compression by a factor of 3/2. Now you'll notice that 3/2 is the reciprocal of 2/3. It's just the way that I'm describing it, vertical compression by a factor of 3/2. If you want, you can say vertical stretch by a factor of 2/3, but which is grammatically accurate, but we'll talk more about that tomorrow. Okay, let's leave that there for now. Okay, next would be this negative that's on the inside. So this negative on the outside is vertical, so this negative on the inside of these brackets is your horizontal reflection. That's a reflection in the y-axis. And oh, I should tell you that this example is on the sheet that you started the other day, so you might want to record it there. Sorry, I should have told you that first. Okay, and then next on the inside you have this 4/5. So that 4/5 is a value that is between -1 and +1. So meaning that it's a small value of k. And remember how we talked about a small value of k actually causes a stretch. So it's opposite of what you think. So it says 4/5, that's a small number that actually causes a stretch. So notice that a small number in the vertical caused a compression, but a small number in the horizontal causes a stretch. Okay, and again we say by 5/4. I'll talk to you tomorrow about that because I know that's really going to confuse you, but let's just talk about the math and not about the language. Okay, next would be this. We see it says x minus 6. That's actually going to cause us to move right by 6. So opposite of what you think. It says x minus 6, but we're actually going to move right. And then this last thing on the end is this +7. That's going to move the whole thing up 7. So vertical shift. Okay, second example on that same paper. Again, it says state the parent function and list the transformations applied to it to obtain this new thing, which like looks really, really, really crazy. But at the heart of it, it's really all, hopefully you can see, the really important part of this is this right here, this magical square root. So because there's a square root sign here, I know that this is a root function. Okay, now the first thing we have to do before we state all of our transformations is to factor out this k value because, sorry, I'll back that up just for a quick sec. So you'll notice that we would normally put, this would be a, oh, you can't see that because it's yellow. Let's go with green. Okay, so this number out front is your a. This number on the inside, the first one that's being multiplied by x, that's your k. This number on the end is your c. But the number on the inside here is not d because normally we have brackets that separate the x and the d from the k. So I'll just back it up. Oh no, I can't change slides without losing this that I just wrote. But anyway, what you have to do is if you ever see something, a coefficient on the x and no bracket separating them, then you have to factor it out. Okay, so we're going to factor 3 out of the 3x minus 12, which is going to leave us with a 3 and then x minus 4. Okay, because 3 times x is 3x and 3 times negative 4 is negative 12. So that's really important. So now because we've done that, now we can see that our a is negative 2, our k is positive 3, our d is this 4 right here, and the c is the negative 5 on the end. Great. Okay, so the parent function, like I said before, is y equals the square root of x, and I know that because I can see a square root sign. So the only kind of function that has a square root sign that you know about right now is root function. Okay, so the first thing I'm going to list is this negative. I'm reading from left to right. So the negative out front causes a vertical reflection, or reflection in the x-axis. Next, I'm going to look at the 2. The 2 is also part of the a. That's still vertical. It's a vertical stretch because that 2 is larger than 1. Oops, that's supposed to say stretch. Let me just fix that right now. This is not a compression. This is a stretch. Okay, that's all I'm going to get it. ST, stretch, 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 not a compression. Teachers make mistakes too. Okay, so the next thing is K value. Because K is large, that's actually going to result in a horizontal compression. So a large A made a stretch, a large K makes a compression. So they operate in different ways. Next is this D. It says negative 4, so we're actually going to move right by 4. And then here the C on the end says minus 5. We're actually going to move down by 5 exactly as it says. Okay, so everything in red is vertical, everything in blue is horizontal. Everything red, which is vertical, goes exactly as you see it. It works the way you expect it will. Everything in blue works the opposite way. So large K results in compression, negative D results in moving right. Okay, so this is the order that we always do things in. So you have to do your stretches and compressions before you do your translations. Truth be told, these two things can be, you can do your reflections first if you find that easier. But really at the end of the day, as long as you're doing stretches and compressions before your translations, that's most important. And really if you're moving left to right, just do the transformations in the order that you see them, then that will always work. Okay, so that was really where I was hoping to finish on Thursday. So these were the things that we were going to look at, which was basically just figuring out what transformations have already happened from looking at the graph or looking at the equation. And then today, what I really want to look at is actually performing those transformations, so applying transformations to a parent function. So basically you're taking something boring like y equals x squared, and then you're going to add pizzazz. You're going to make it more interesting. Okay, so what I'd like you to do right now is I'd like you to choose one of these two examples, and I'd like you to list the transformations applied to the parent function. So here the parent function is a parabola, and here the parent function is a root function, but it doesn't change the way that a, k, d, and c operate. A, k, d, and c. So I'd like you to choose either one of these right now, and then pause the video, and then everybody take a second to list the transformations that would be applied. You can choose the one that I've called rare, or you can choose the one that I've called well done. Obviously the well done one is a little harder, so if you're a little nervous, start with rare. So go do that, pause the video, and then when everybody's ready, put it back up again, and then I'll take them up with you. Okay, so you should be at the place where we're taking this up now, so let's do it together. Okay, so on this one, the parent function is y equals x squared. This 4 out front is a vertical stretch. I'm going to just do shorthand because it's really hard to do this on my computer. Vertical stretch. Oh, maybe I can do the word stretch. Okay, and that's a vertical stretch by a factor of 4. Okay, next on the inside is that 2, and I know that that 2 is actually the k value. So that's going to cause a horizontal change. So that's because that's a large number, it's larger than 1, that is actually a horizontal compression by a factor of 2.